Hello everyone, and welcome to our Windows 365 Meet .NET Aspire session at the .NET Conference 2025. My name is Eric Guo, and I'm the Principal Group Engineering Manager for Windows 365. I'm excited to be here and share how we are advancing productivity in complex microservice environments.
And I'm Chuanbo Zhang, Principal Software Engineer and Architect for Windows 365. Together with Eric, we will walk you through our journey integrating Windows 365 with .NET Aspire, focusing on how we tackle multi-repo microservices challenge.
Let's begin by providing the background of our service and the context for why we adopt .NET Aspire and the challenge we faced. The context is essential for understanding our journey with .NET Aspire. So our service, Windows 365, is a DaaS service, offer a personalized, powerful, simple, and secure Windows 11 experience. Users can access their Windows desktop or DevBox from anywhere on any device, with all their apps, data, and settings preserved. This enables true flexibility for remote and hybrid work while maintaining enterprise-grade security and manageability. This diagram shows the high-level architecture of Windows 365. On the left side, you can see users connected from various clients that we offer on different platforms. On its right, Windows 365 service orchestrates compute, storage, and the networking resource hosted on Azure. The service is integrated with Azure AD, Intune, and other Microsoft services, ensure seamless management and security feature. This architecture enables scalable, reliable, and secure delivery of Windows desktop from the cloud. Now let's look at the architecture context for our service. Our tech stack includes App Service, Cosmos DB, Azure Functions, Event Hub, Azure Storage, Service Bus, and Azure App Configure. We have over 50 microservices, each in its own repo, managed by separate component team. All microservices use a centralized shared info, which allows for unified solution. Compliance and security are critical. Microsoft Certified Compliance introduced additional overhead and evolving requirements, making local debug and testing essential. Service dependencies are complex, including Intune, ARM, Graph, AAD, Cosmos DB, and Event Hub. With this context, the team has urgent need for robust local debugging, multiple repo support, and strong compliance measures. Now let me hand over to Chuanbo, who will walk you through the challenges and the solutions when we integrate with .NET Aspire.
Thanks, Eric. Now let's look at how Windows 365 integrates with Aspire, especially to address the challenge with multi-repo microservices support. This section will show how Aspire helps us manage complexity with local debugging and testing. Here is an architecture overview diagram for Windows 365 integration with .NET Aspire. As mentioned previously, we use microservice architecture, with each microservice team using their own repo. To facilitate that, we also suggested each microservice owner to create app host and service default, as well as a test project in their solution, so their experience will be ideal, that they just focus on their own repo for the daily work. We have a shared info team, and we provided multi-repo support from the shared info repo. For engineers working on a particular service, they have the F5 experience of just clone their service repo locally, click the solution file to open with Studio, and then press F5 key to launch. Our engineers use DevBox for daily development, and the environment is already pre-configured with necessary tools like Docker Desktop, WSL, Visual Studio, and GitHub Copilot. So this F5 experience with Aspire is ideal for them. Our intern and new hire could quickly onboard and start to productivity right away because of this support. This mini cloud PC sample demonstrates a multi-repo setup. 3 local projects from this repository, 3 microservice dependencies from another sample repo, and a third container running customized Azure Resource Emulator. With this setup, we can develop and test complex scenarios without requiring access to all real cloud services. These are the actual samples we use internally, designed to closely replicate real microservice interaction pattern without risking exposure of internal code. Let's see this in action with a quick demo.
Now I'm going to demonstrate the usage of .NET Aspire in Windows 365. In this demo, we'll be working with two sample services, Mini CPC as our working service and Cloud Device, a dependent service. These services are hosted in separate repositories. Let's start by opening the Mini CPC project in Visual Studio. Inside the app host project, we've defined several resources in program.cs. First, we define EmuHub, an Azure resource emulator provided by the Windows 365 team. Then, we define other resources such as Cache, Cosmos DB, Event Hub, and App Configuration Emulators. Since we've already published an image for the Cloud Device service, we can easily add it as a dependency using the AddMicroservice extension. This service will be loaded into Docker as a container. Next, we add another dependency service called Provision Policy. Since its image isn't ready for containerization yet, we'll run it as an emulator and mock the response for one of its frequently used APIs. Finally, we add directory, Cloud PC API, functions, and admin portal projects. Now, let's start debugging with F5 Experience. The Aspire dashboard automatically pops up. After a few seconds, we can see all services are running now. To provide some initial test data, we implement a function named seed data. There are two types of seed data. The first type is Azure App Configuration Data. We define test data in this nd.json file. It will be automatically imported into the App Configuration Emulator. The second type is Cosmos DB data. It is defined in a JSON file, which is automatically loaded into Cosmos DB. Let's go to the dashboard. After clicking the Data Explorer, we can see the test data has been imported. Next, let's launch the admin portal. Here, you can see a list of provisioned cloud PCs from seed data. Now, let's create a new cloud PC. When we click the New Cloud PC button and set the device name and username, the application calls the Cloud Device service to retrieve available devices. Service Discovery will automatically locate the correct endpoint. We can see the response coming from the local Cloud Device container. After that, the app calls the mock provision policy service. There is a predefined mock response in the emulator templates folder. This mock provision service will return the response. Once we continue, the system uses this mock response to provision a new cloud PC, and as you can see, the cloud PC is successfully provisioned. Thanks for watching this demo video.
Here is a recap of the flow we just demonstrated. Engineers could launch local debugging with simple F5 experience, or manually test by trigger from HTTP file and eventually run as test automation. App host will launch the microservice and its direct or indirect dependency through microservice container or emulator, and we could load Azure resource with emulator as well. We also have Azure support for official dependencies such as Cosmos DB and Event Hub. In addition, we've built custom microservice emulators and implemented service discovery to support development and testing across multiple repos. To provide reusable development experience, we developed seed data import-export. To support test automation, we also completed integration with CloudTest to enable automated end-to-end testing. To make it easier for adoption, we also developed AI-assisted migration to help accelerate the adoption of existing legacy test cases. Resource is a fundamental piece in Aspire app model. Aspire provided three main built-in resources type: project, executable, and container resources. On top of the container resources, Windows 365 E14 provided microservice resource abstraction to simplify microservice team experience with AddMicroservice extension for direct dependency. Under the hood, AddMicroservice will take one parameter of the service lane in most simple cases. and add container resource with image based on this microservice name from central shared either container registry and the default latest tag. In advanced use case, feature team could specify different tags to load specific versions. The microservice image is published as part of the release pipeline. Each microservice publisher its container image to a shared either container registry, allow Aspire to pull and run this image during local debugging. This setup enables developers to work within their own repo while seamlessly integrating dependency services. CI pipeline augment image publishing, and echoes project within each repo define the necessary resources, ensure consistent environments. Even with container support, trying to run all possible dependency services isn't practical. If you have a deep chain, say service A depends on service B, which depends on service C, and further depends on service D, etc. At some point, you'll be running dozens of microservices containers just to test one service, which is slow and resource intensive. So we need some mechanism to terminate the dependency tree. Instead of launching every services as container, we need to short circuit certain dependencies by simulating them with an emulator. For this, we use microservice emulator support with RunAsEmulator extension against the microservice resource. Behind the scene, RunAsEmulator will replace the container image from real service image to a shared emulator image and pull the HTTP template from real service image and local corner service could override. The emulator container is essentially a lightweight HTTP mock server which loads HTTP response templates. We leverage WizStudio's HTTP file template with a minor adjustment to support HTTP response template. For distinguish, we use the .rest extension for the template. Within template, response header, response bodies are specified. We also support to bundle multiple response templates together with the same triple-shot non-compilator. In addition, you could also do variable replacement, as you could see in the right side of $query $route to replace a request value from query stream or URL route. You could define your own variable as well. This HTTP file-based template is very easy to use for microservice team. In most cases, they just capture the HTTP traffic and save as .rest file to use as emulator. By emulating non-critical services, developers can focus on testing core functionality without the need to run entire dependency tree, significantly improving efficiency and reducing resource consumption. Each microservice team is encouraged to bundle their own REST template into their service image for any upstream service that might call them. For example, if service C is commonly called by others, the team maintains a set response example in REST files format. This gets included either in the image or a shared repository, so an emulator could use them. Microservice emulator logic will first check the real service image for a template and also allow the calling service to provide an override if necessary. Using the emulator, the dependent service tree can be truncated. In an example, service A depends on service B for direct dependency, and C for indirect dependency with service B. We run service B as a real container. We'll add service for service B. And we run service C as an emulator. We'll add microservice and run as emulator. Now service B will actually call service C's endpoint, but that endpoint is handled by emulator with canned response. So we didn't need to spin up service C's code at all. This dramatically reduced the number of services running while still simulating their behavior. In summary, the microservice emulator provides a way to simulate services that are not critical to test in depth for given scenario. We use built-in emulators for services like Cosmos DB and Event Hub, and extend with HTTP file template for others. Microservices also rely on Azure resources, and Aspire offer built-in support for many of them, such as Cosmos DB, Event Hub, Azure Storage, and Azure App Config. However, there are some resources we use, like Azure Key Vault, AAD, ARM, and MS Squad, that aren't yet natively supported. For this, we applied the same REST file template and packaged them into a common emulator hub image for the microservice team to utilize. Microservice team could also override those templates to customize for their needs. Up to now, we have introduced 3 techniques we use to load dependencies locally: microservice container for direct dependencies, microservice emulator for indirect dependencies, and Azure resource emulator for Azure resources. This approach eliminates the need for live cloud access during local testing. With those, we could now run the service locally and debug with F5. For microservices resources, we provide client library that integrate with service discovery to locate and call its dependencies. This is implicit for all service-to-service code, and coding with reference is optimal. To provide optimal experience and reduce boilerplate code for microservice owner, internally we use a service map to maintain the info and resolve the endpoint from Aspire. As service and emulator start, their address are populated into the service map, accessible by the info library. This enables seamless service-to-service communication without manual configuration. The integration ensures that microservices can discover and interact with each other in the local environment, just as they would need in production, maintaining consistency and reducing setup errors. Another component identified was test data setup. Many microservices rely on having certain data in Cosmos DB or other stores to function. Traditionally, the microservice team spent considerable time manually preparing test data, which is a repetitive task. To streamline this, we've introduced seed data support using Aspire lifecycle hooks and the application app model feature. Each microservice repo can include a set of JSON files or folder representing seed data. Upon F5 launch, Aspire will detect this and load them into the local Cosmos DB emulators. This ensures developers start with a consistent state and easily access the necessary test data, simplifying validation and development workflow. Developers can make changes or generate new data during testing and then export it via an Aspire dashboard button or command to update these seed data files. This makes it easy to capture new test cases or configuring as code. Overall, this saves time and prevents errors by providing out-of-box test data. Ensure every developer, when they start with a consistent known good state in their local environment. We use app config and want seed data support extend to app config as well. Luckily, with Aspire 9.5, the latest AAC emulator are added, and we quickly try to leverage AAC support and checking the ND JSON file with each line as one JSON config. As this is natively supported, we don't need any custom logic, but able to make the config ready out of box for testing. Aspire end-to-end tests are executed in Cloud Test as an integrated part of the CI/CD pipeline to ensure that only high-quality and stable builds are promoted. Specifically, we utilize XUnit and ADO agent pool with preconfig image containing Docker container to facilitate the Aspire end-to-end testing on Cloud Test. ADO agent run Aspire in headless mode, launching services and execute test suites in isolated environment. This cycle validates scenario without relying on shared integration environment. This test is incorporated as a prerequisite for pull request merge, prevent buggy code to check in. There are a few learnings I want to share here. First, for project resource, you need to copy the source code to the Cloud Test working folder. Otherwise, you will hit exception when trying to add project resource. Second, set correct dependencies reference and waiting, especially important to add house check and ensure house state before test run. And lastly, also need to pay attention to the differences of local run with Wood Studio versus Cloud Test run with direct test command. And also pay attention to the low launch profile used for Cloud Test. So with this integration, we've dramatically improved developer productivity and reliability. Now, I'm handing over to Eric, who will share our productivity improvement result and future aspiration.
Now let's talk about how .NET Aspire has surcharged our productivity. By integrating Aspire into our workflow, we have been able to streamline development and the testing lifecycle across our microservice landscape. This has enabled our teams to move faster, onboard a new service more easily, and maintain high quality as we scale. Aspire enables developers to work in a consistent and isolated environment by locally launch all dependent resources with a single F5 click. Developers working on each component now can launch and debug their microservice with its dependency locally in minutes instead of waiting hours for cloud deployments. This feedback loop compressive means issues are found and fixed much faster. One engineer noted they could reproduce and fix complex issues in one session locally, which in the past could have taken days with the old method. This simplified approach removes the need for complex environment configuration, dramatically improving development efficiency and reducing debug time from hours to minutes. Developer satisfaction improves, and engineer surveys reported higher productivity. The initiative resolved the critical pain points, streamlined workflows, and improved overall productivity and quality. By enabling true local testing, it eliminates the slow coding, checking, deployment, and testing cycle, and let engineers iterate much faster. To summarize, dramatically faster debug cycle, better overall quality because we catch integration issue much sooner. And the developers are much happier now that their top pain point is gone. This success demonstrated the value of investing in local debug tooling for large-scale cloud services. It has been 6 months since we started adopting Aspire. So far, we have onboarded 15 microservices, with more in the pipeline, thanks to the positive feedback from our teams. 4 of these microservices are already running end-to-end tests in Cloud Test, with over 150 test cases executed. This adoption has not only improved our test coverage, but also accelerated our ability to deliver reliable features to our customers. Key lessons from this integration includes the importance of framework extensibility, team buy-in, and the balance fidelity with simplicity. Leverage extensibility. .NET Aspire's design provided hooks to extend it for Multi-Repo, which proved invaluable. By creating customer resource types and emulator logic, we achieved the scenario without forked version of Aspire. Microservice team buy-in. It was crucial to get each microservice team on board. For example, adding app host projects publishing containers, writing REST templates for their APIs. This was achieved by clear guidance and demonstrating value. Once a team saw that with a little bit upfront work, they could avoid int deployments for testing, they were eager to join. Balancing fidelity and simplicity. The combination of real containers for critical dependencies and emulators for others was key. Not every dependency needs to run for real in every test. Identify which services and resources can be safely mocked to reduce complexity. This keeps the dev loop lean. Provide easy way like one-line RunAsEmulator to swap between real and mock as needed. Continuous collaboration with framework team. The Windows 365 team engaged with the .NET Aspire product team throughout. This continuous collaborations with the Aspire team ensured alignment and the rapid adoption of new features. Phase the rollout. Starting with a pilot, the mini CPC example and one real service helped to prove the concept, then expanding to more services. Incorporating their feedbacks each time allowed the project to mature. By integrating .NET Aspire and extending it to handle Windows 365's multi-repo microservice architecture, the Aspire integration delivered a game-changing local development experience for the team. Looking ahead, we are eager to adopt the latest .NET Aspire features as they become available. One capability we are particularly excited about is Dev Tunnel, which enables a local service to be exposed as an online endpoint. By defining customer workload selectors, developers can seamlessly enable a powerful and convenient hybrid debugging experience. This approach is especially valuable for scenarios with complex dependency requirements. What's more, we are planning to integrating Aspire with Playwright for UX testing and with WireMock for more advanced and complex service simulations. We are also exploring how GitHub Copilot together with Aspire could help assist with Aspire configuration or test generations. For example, helping generate REST templates or diagnosing issues while Aspire's tracing data. While we currently focus on dev tests, Aspire's model might extend to one-click deployment to a test environment as the next step, aligning closely with the production configurations. Besides, we are also looking for how Aspire test for runner and the deployment scenario can further enhance our workflow. Our goal is to continue pushing the boundary of productivity and quality in our cloud-native development. That brings us to the end of our session. Thank you all for joining us and learning about our journey with Windows 365 and .NET Aspire.
We hope you found our experience and solution helpful. Feel free to reach out if you have questions. Enjoy the rest of the conference.